my first thing that I wanted to go over with everybody is any questions. So I know that we left off having tons of fun on Monday with all of our solving equations. I know. Elijah says you got to love the window to the soul of the computer. I know. The screenshot of the screenshot of the screenshot just keeps going. Does anybody have any questions they want me to go over? I'm happy to do any problems. If there's one that's you're stuck on that you're trying to get through, I'm happy to do that. Anything? Everybody getting caught up, I hope. I know. I don't know what that means. If that means you guys are all good, or you're like, I haven't quite got there this month or this just yet. Everybody else. So Elijah's working his way there. How's everybody else doing? You guys doing okay? I can't hear anybody if you happen to be talking too. All right. Daniel says he's giving me a thumbs up. He's doing good. No questions. Awesome. Okie dokie. Well, then what, excuse me, what we're going to do today is we're going to go over 3-5 since we did one section on Monday. And like I said, it's going to be a long section. I realize that, but we are going to go ahead and go over the next section today so that we can, on Monday, we can keep going with something called matrices. So this is often something new for Algebra 2 students. If you've seen it before, that's great too. So we're going to talk about a matrix, or sometimes in the plural, the matrices. Okay. And so what is a matrix is the first question you can see posed up there. And you can see I stole all of this from a website called mathisfun.com. So obviously math is awesome, right? There's a website out there that says math is fun. Okay, so a matrix is basically, well, you can see it right there, an array of numbers. And it can be any size. This particular matrix that you see here at the top is called a 2x3 matrix. And I will explain why that is when I can get my pen working here for a minute. That's not what I was trying to do. Oh, now you want to draw. All right, close that. Yes, there is a reference to a movie. All right, so a matrix, this particular matrix has 2 rows. So we consider the rows go this way, right? And 3 columns. So that's how we name a matrix. We name a matrix by the number of rows and the number of columns. So this also, if you use Excel a lot, which I'm sure you guys do, rows and columns just the same way as an Excel document, right? So for example, if I had a matrix that looked like this, 3, 2, 1, 5, 0, 4, this particular matrix that I just drew has 3 rows, all right? So this is a 3-row matrix, and it has 2 columns. So we call this a 3x2 matrix. All right, and what the purpose of a matrix is, I don't have it written on here, is that this is a way that we have, when we have lots of data to analyze or lots of data to hold, that we can organize the data and we can do some operations on that data. Okay, so we started off saying, okay, well, we have one X and Y that we want to figure out, and then we move to X, Y, and Z. Well, what happens if we get to W, X, Y, and Z that we want to solve? You could have 4 equations and 4 variables. That would be really fun to do all that algebra, right? Well, the whole idea of matrix operations is that we can actually hold lots of data in a matrix, and then we can actually perform operations on that. And by operations, I mean we can add and subtract data together. We can multiply and divide it together. Okay, not the other kind of operations. Okay, so the simplest thing that we're going to learn to do with matrices or a matrix is to be able to add them together. Okay, and this is actually pretty easy when you see it. So it looks intimidating, but it's easy peasy. So to add or subtract two matrices, add the numbers in the matching positions. So they must be the same size matrices to add or subtract. So this is going to look obvious when you see it. Okay, so I have here, this is a 2 by 2 matrix, right? It has 2 rows and 2 columns. And then I have a second 2 by 2 matrix, 2 rows, 2 columns. And when I add them together, it's going to give me another 2 by 2 matrix. So what they're doing here, you can pretty see, I think that they made a nice little picture for you, right? You're going to take the number in the first row, first column, which is 3 of the first matrix, and then the number in the first row, first column of the second matrix, and you're going to add them together. So 3 plus 4 is 7, and that's going to go in the first row, first column of your final matrix. Okay, so let's pick another one. If we take our second row, second column, number 6, right? We have to add that to our second row, second column of our second matrix. So 6 plus -9 gives us -3. Expanded addition. That's one way to look at it, Elijah, right? Just going to add in the same place. So what they mean by the two matrices must be the same size is pretty obvious. So if I have a matrix that is, I'm going to copy this one, 3, 8, 4, and 6. Okay. I have this is a 2 by 2 matrix, right? And I want to add it to a 8 and 4. Okay. This matrix has 2 rows and only 1 column. I can't do this. Okay. The only way this is not possible to do, can't do, X it out. The only way that you can add two matrices together, two matrices together, is if you have the same size. Okay. And then the same goes for subtraction. I don't have the example on here, but if you had a minus sign in here, then you're going to do 3 minus 4. And you're going to do 6 minus a -9. I think that's pretty straightforward, right? No, Daniel says, are there any secret rules? No secret rules for this, other than the fact that for adding and subtracting, they have to be the same size. Eventually, there'll probably be some secret rules, right? Probably eventually. All right, so that is adding. So you couldn't add a 2 by 2 with a 3 by 3. Nope, can't add them together. Have to be the same size. Yep, even if they're in their appropriate positions. Yep. That's pretty good, right? You don't have to deal with all of the, as long as only if they're the same size, then you actually have to add or subtract them. Okay, so that's called adding. So what we're talking about matrix. We're talking about what we can do with them. And then eventually we'll get to why it's powerful in algebra. So we're just kind of like learning what it is and what we can and can not do to a matrix. Okay, that's kind of the big picture. And then eventually we're going to actually use it to solve problems. So it's kind of building up to that. If you're wondering, why do I have to learn this? Okay. We're going to talk about something called scalar multiplication. So this is also allowed in the world of the matrix. Okay, so scalar multiplication means that you're going to multiply a matrix by a constant, which is called your scalar. So this particular matrix, this 2 by 2 matrix, is getting multiplied by 2. Okay, and it doesn't have to be 2 because it's a 2 by 2 matrix. You can multiply by anything. This could be a 10 out front. Any of that's okay. So scalar multiplication just simply says that we are going to multiply every item in my matrix by the scalar. Okay, so what that means is we have this 2 out front, right? First row, first column is 4. So we're going to say 2 times 4 gives me 8. And that goes in the same position as my 4. Okay, and then we're going to keep going. The next one, we'll use purple, right? We're going to take 2, and then we're going to go to our first row, second column. Okay, 2 times 0, and that result is going to go in my first row, second column, same position. Okay. Then, big surprise here, right? We're going to move on to the second row. So we're going to do 2 times 1, which is my second row, first column. 2 times 1 is 2. That goes right here. Okay. And then we're going to go to my, that already did that color. I'm going to go to my second row, second column, and I'm going to do 2 times -9, which gives me -18. Okay, so that's called scalar multiplication. That's when you take a matrix and you multiply it by a single, you call that a scalar constant value. Okay, Elijah says, wait, so all are we doing is proving that it is true? No, we're not proving it's true. We're just learning how to deal with the matrix because you might not have ever seen them before. It's all right. You guys know how well I can do that stuff. Okay, so yeah, all we're doing here with this section and the next section is learning what we are and aren't allowed to do with a matrix. Okay, so we can add and subtract them if they're the same size, and we can multiply them by a constant. And I think those are pretty straightforward with how you do that, right? So I think we're going to do a couple examples here of those. Yes, fancy. We've got a couple examples here. Okay, so first, number 1, we have a 3 by 2 matrix, right? And the reason, let me just give you a heads up. Let me give you a heads up on the size of the matrix and why I keep calling out which size is. The size of the matrix is going to be really important when we get to multiplying matrices together. So that's why I keep calling out what size it is. So get used to trying to figure out, is it a 3 by 2 or a 2 by 3? So this is 3 rows, right? 3 rows by 2 columns plus a 3 by 2. And you guys can obviously visually look at it and see that these two matrix are the same size. So we are allowed to add them together, right? So you guys can try this on your own at home because I don't think it's too difficult. I'm going to do it here too. And I have to make my answer matrix a little bigger because I can't write that small. So what we're going to do is we're going to add the numbers that are in the same position of the matrix. Okay, so we are going to take the first row, first column. We've got 5, right? And first row column of the second matrix plus -8. So 5 plus -8 is -3. Okay. Then we are going to take, this is what I should be doing. I know what I should be using. I should be using the highlighter so I'm not making a mess here. Then we're going to do the first row, second column. Okay, so the first row, second column is 2 plus 10. So that's 12. That's not going to help if I write it like that. That's 12, right? Okay, and then we're going to do the second row, first column, -1 plus -6, and that gives us -7. Guess I have to check my work because I'm changing colors like crazy. Okay, second row, second column is going to be 8 plus 3, right? 8 plus 3 is 11. Okay, next up we have our third row, first column. So 4 plus 2 is going to give us 6, right? And last up we have our third row, second column. So we have -5 plus -1, which will give us -6. Okay, so for those of you that actually try this at home, is that what you ended up with? All right. Elijah, this is painfully simple. Better painfully simple than painfully hard, right? Oh, we're doing as a bunch of addition. All right. Well, I'm glad that it's painfully simple. We could use that after the last section, right? Okay. Number two. Number 2 should be painfully simple as well. It's also a smaller matrix, so that's easy, right? So these are both 2 by 2. This is a 2 by 2 and this is a 2 by 2. You will notice that it is a subtraction problem, so you want to make sure that you do the right one when you're calculating these, right? Okay, so let's do this kind of quickly. Our first row, first column has 1.2 minus 2.4. Okay, so I end up with -1.2. It's crazy too. Our first row, second column has 5.3 minus -1.6. So that's like adding 1.6, right? So we're going to get 5.9. Okay. Our next row, so we're on the second row, first column. Okay, we've got 6.1 minus 0.1, so that's just going to leave us with 6. And then our second row, second column is 4.4 minus 3.1, which is 1.3. So we'll take this, right? Nice, easy section so far. So far, so good. All right, so let's look at number 3. Number 3, we have something a little different, right? This is our scalar multiplication. So scalar multiplication means that we're multiplying a single number by the whole matrix. That means what we need to multiply everything in the matrix by 2. So 2 applies to every number in the matrix. We're going to scale, like scalar multiplication, we're going to scale everything up by 2 is how I like to think of it. Okay. So that means that when I do this, to be overly obvious here, what I'm going to do is I'm going to multiply 2 by -1 in the first position, right? In my first row, second column, I'm going to multiply 2 times 4. In my second row, first column, I'm going to multiply 2 by 3. And in my second row, second column, I'm going to multiply 2 by negative 6. Okay, so 2 times negative 1 is negative 2. 2 times 4 is 8. 2 times 3 is 6. And 2 times negative 6 is negative 12. Any questions so far? You guys feeling good? Not too bad. You guys ready for the challenge problem number 4? All right, so number 4 on your paper says solve the matrix equation. So like, whoa, wait a second, where did all this come from? I thought I was just learning to add and multiply, right? But you can actually solve this given all of the knowledge that we have. Okay, so let's figure out how to solve this guy. So what's your first question? How do we solve for the variables? That's a great question, Elijah. So this is what we're actually going to do. It's kind of like actually solving. Yeah, it's kind of like treating it like a normal equation, right, Elijah? We need to get to a point where we solve for x and y. But right now, a bunch of things are happening to x and y, right? Right now we have 2 times this matrix, and then the first matrix is being subtracted from the second matrix. So we're not quite there, Elijah, to say negative x minus 9 equals 4. We're not quite there yet, but we're going to get there. Okay, so what we're going to do is we're going to simplify what we have a little bit, and then I'll show you how we can solve. Okay, so the first thing that we want to do is just like we would do in order of operations. We have 2 things that are happening, right? We have 2 multiplied by the first matrix, and then it's subtracted by the second one. So we want to do the multiplication before addition and subtraction, just like we would do in a regular equation, right? So what we're going to do is we're going to scale up this first matrix by multiplying everything by 2. Okay, so this first equation is going to become 2 times 8. And then the second, or sorry, I didn't even start. The first row, first column is 2 times 8. The first row, second column is 2 times negative x. Okay. The second row, first column is 2 times 5. Second row, second column is 2 times 6. Okay, so what I did is I'm trying to simplify this first matrix that's being scaled by 2. Nothing is happening with my second matrix. So I've got 3, negative 9, 10, and negative 4y. And then the rest stays the same. We'll carry that down. So let's simplify this, okay? So we've got 2 times 8, that's 16. We've got 2 times negative x, so it's negative 2x. 2 times 5 is 10. And 2 times 6 is 12. Okay, so now we have these 2 matrices that are being subtracted. Okay, and do we know how to subtract 2 matrices that are the same size? Yeah, right, since they're the same size, we can do that. So what we're going to do is we're going to try to leave a little space here. We're going to subtract the 2 matrix and get a resulting 2 by 2 matrix. So we're going to do 16 minus 3 is my first row, first column, right? We have negative 2x minus a negative 9. Yuck. We've got 10 minus 10 for our second row, second column. And we have 12 minus a negative 4y. Okay. So let's do some simplifying. 16 minus 3 is 13. Negative 2x minus a negative 9 is negative 2x plus 9. Yes, the 2 only applies to the first matrix. Good question, Elijah. 10 minus 10 is 0, and 12 plus 4y. Okay. So now I didn't bring my equals all the way down because you would have to painfully watch me rewrite it. But remember our equals up at the top goes all the way down here. 13 4 0 and 16. Well, that's a good thing that happened, right? Because what we have is two matrices that are equal to each other. All right. And when we did all of our work of multiplying our scalar by the first matrix and then subtracting the two matrix, then we get the first column has 13 and 0 in it. And our answer has 13 and 0. So that means that we actually did the work correctly, right? So can you see 13 equals 13, 0 equals 0? That means that negative 2x plus 9 equals what? It equals 4, right? Because they're in the same position. This is our first row, second column. And we have two matrices that are equal to each other. So that means that the ones that whatever position each is in equals each other. Right? Do you guys follow what I'm saying? So that's totally not, that's not a highlighter that's going completely over the top. All right, let me rewrite that. Negative 2x. So this position, let's have to circle it, of the first row, second column is equal to this position. So that means if I make some room over here from this mess, that I could say, and that's also not what I want to do. Negative 2x. So I'm taking what is in my first row, second position. Negative 2x plus 9 equals 4. And can we solve this? Yeah, right? So we need to subtract 9 from both sides. So we get negative 2x equals negative 5. Divide by both sides by negative 2. And you get that x equals 5 divided by 2. Okay. And then the same thing with our last position here, right? Our second column, second row. We have 12 plus 4y is equal to 16, right? So we have 12 plus 4y equals 16. We need to subtract 12 from both sides, and we get 4y equals 4, or y equals 1. All right, so how did you guys feel about that? Hi, Greta. Do you feel like you want to see another example like that? Or do you feel like, I think I can get it? Nope to another example, James? You think you're good? Elijah says it's easy. It's easy, but it looks complicated. Yeah, that's true. Yes, the matrix makes it look more complicated. I will agree to that. All right, well, you have a few of your problems that'll have you solve for X and Y. If when you saw it, like, no. Oh, good. I'm glad everybody's on the same page with this. Sometimes when I introduce what a matrix is, people are like, and just the whole idea of it kind of throws them off. So you guys are already ahead of the game. I do want to show you in your book, if you happen to have it with you, I want to show you more on page 191. So I want to show you one way that they actually identify how to do these problems. I think you guys will be able to figure it out. So I think what I really need is to take a screenshot of this and post it. And erase all this craziness here. Okay, so if you happen to have your book, page 191, problems 16 through 23, well, you'll be doing 17 through 23. So what they have done is they give you a set of a matrix. So they say matrix A, and this is how you name a matrix. So we didn't explicitly talk about this. So they say matrix A is 5, 3, -4, -1. Okay. So they call that you can name a matrix by a capital letter. So if you see this notation, you'll know what it means. Okay. And they tell you matrix B equals 18, -12, -6, 0. And then they tell you that what matrix C and D equal as well. Okay. So again, this is on page 191 in your book. 191. If you're doing your homework and you get there like, oh, okay. So if then the problems below say something like this. Number 18 says solve, use matrix A, B, C, and D to evaluate this expression. So they say for A, so you see the capital A, minus B. So what I think is interesting about this is that this looks like our equations that we solve for X and Y, right? And when we use X and Y, we use a lowercase x and Y. But when we use a matrix, we use capital letters. So that's one way that you can tell what you're doing if you're using matrix or variables. But the other thing I think is interesting is it kind of introduces the idea that we're able to not only deal with a single piece of data, one X and one Y, now we're dealing with a lot of data. I mean, A and B happen to be 2 by 2 matrices, but they could be a 20 by 20 matrix, and they still have the same properties. And there are calculators out there, obviously, that are going to help you calculate big matrices. They're not going to, you don't have to sit there and add 20 by 20 matrix together, although you could, right? So if we have something like number 18, what we're going to do is we're going to substitute in our matrices, and we're going to do the same, excuse me, the same operations that we would do if it was just a single X and Y. So what I mean by that is if we have 4A minus B, that means we're going to say, okay, 4, and matrix A is 5, -4, 3, -1. Did you just tell us to use your calculator? I did not. I was just telling you that there are calculators that can do it. Actually, this is one area in which your beloved Desmos fails us and is not very good with matrices. I know. fails us. Your old trusty TI calculators, if you have one, will do matrices, but Desmos, last I checked, does not do matrices. Or if they do, it's really clunky. Okay, so I think you guys all get this, right? 4a, 4 times a minus b, just simply means you're going to take matrix A and matrix B and you're going to substitute in, just like we would substitute an x and a y. And then we have to do the operations, right? And when we do operations, we're going to do it in the same order we do an equation, right? You wouldn't subtract first and then multiply by 4. You're going to multiply by 4 and then subtract, just like your order of operations, right? So we have to multiply 4 by everything in the matrix. So 4 times 5 is 20. 4 times negative 4 is negative 16. 4 times 3 is 12. And 4 times negative 1 is negative 4. Minus 18, minus 12, minus 6, 0. Okay? And then we're going to subtract, right? 20 minus 18 is 2. Negative 16 minus a negative 12 is negative 4. You guys have to check me because I'm doing this off the top of my head. 12 minus a negative 6 is going to give me a positive 18. And negative 4 minus 0 is negative 4. All right. So that's how you do those. I just wanted to be aware of what that looks like as an equation. Okay, so everybody good on that? Yep. Okay, I want to show you a tiny bit of 3-6. That does not mean I'm assigning it to you yet because we're going to do more on Monday. I mean, if you really feel like going for 3-6, go for it. But I just want to kind of give you a preview so your brain starts thinking. So when you come in Monday morning and I show you 3-6, you're not like, what happened? Yeah, 3-4. I know, Greta. 3-4 is tough. Okay. So what we're going to talk about, we talked about adding and subtracting matrices, no problem, right? We talked about multiplying a matrix by a scalar. So we're scaling it up or down depending on what number, right? 3-4 is awful. I know, I'm sorry, 3-4. It's just a lot of math, right? So what I want to talk to you about is 3.6. What we're going to talk about is multiplying two matrices together. Okay. So this is where I was talking about, you know, how I was like making a point of saying what size every matrix was. This is where it becomes important. So what you do when you're multiplying matrices is that you have to make sure that, let me see where it is written on here. Okay. You have to make sure that the number of columns in your first matrix is equal to the number of rows in your second matrix. Okay, so this is kind of the idea that I'm going to introduce, and then we'll do some practice on Monday. All right, so we're not going to totally dive in. So what I mean by that is that, see here, we have these two matrices that are being multiplied together. So those rules about having the same size matrix when you add and subtract don't apply when you multiply. Okay, so you can see here that this is a 2 by 3 matrix, right? It's 2 rows and 3 columns. Okay, and our second matrix is a 3-row by 2-column matrix. So obviously they're not the same size. So if I wanted to add these two together, can't do it, right? I can, however, multiply them together because in order to multiply two matrices together, they have to have basically these two numbers right here have to match each other. And what these numbers represent, this represents the number of columns, right? We have 3 columns. The number of columns in the first matrix has to match the number of rows in the second matrix. If these two match, then you're allowed to multiply. Okay? And the result is going to be a 2 by 2 matrix. Okay, so it's a little hard to think of. That's why I want to like introduce it and then we'll go over it again. So what we're going to do, it's kind of crazy. So I'm just going to do 1 today. You're going to multiply this whole first row by the whole first column of the second matrix. Okay, so in order to find our first row, first column, you're going to multiply the first row by the first row in the first one by this first, oh gosh, let me start over. In order to find the first row, first column over here, okay, you're going to multiply the first row of the first matrix by the first column of the second matrix. That's what I was trying to say. And what you will do is you'll say 1 times 7, it's written right here for you, 1 times 7 plus 2 times 9 plus 3 times 11 gives me 58. Sounds fun, right? So then in order to find let me switch colors. This is going to be our first row, second column. Okay, to find the first row, second column, you're going to multiply the first row of your first matrix by the second column of your second matrix. So this is first row, second column, first row, second column. They do kind of match up, right, in terminology, but it's thinking through the problem. So then to find my, completely switch colors here, to find my second row, first column, I'm going to multiply my second row times my first column. And to find my second row, second column, I'm going to multiply my second row by my second column. Okay, so I just wanted to kind of give you a sneak peek why I was being, back when we were doing addition and scalar multiplication and all that kind of thing, why I kept saying like, oh, this is the first row, second column and all that kind of thing and what size it is. It's because when you get to multiplication, you got to kind of remember those. So as you're doing 3.5, kind of in your head think, okay, which position am I in, and kind of name it for yourself so that when you get to 3.6, it'll be a little bit easier. Did I scare everyone, or does it feel like, maybe it's doable? James says that here's why matrix is not easy as you thought. Yeah, basically, it's possible, right? Don't be scared. It's actually just, it's like a system, right? And we're going to figure out the system and we'll be able to do it. But for now, you just focus on the fun that is 3.4 and 3.5. And in class on Monday, we're going to talk about 3.6. So we'll do a lot more examples with this. And then how it's actually useful for us. That's what really we're going to get to, is how can we use this to actually solve equations? Bigger equations than our three equations and 3 variable equations. All right. Any questions? You guys ready to take on the math world today? No. Daniel, I'll have to look. I am bad. I said that I would have everything graded by Wednesday, and I don't have everything graded yet. So I'm planning on doing that after the help sessions this morning. So I'll be grading after the help sessions. Now you're gonna go wake up. I'll check, Daniel. I'll let you know. All right, well, that's it for today. Just think about 3-5 and how nice and easy that's going to be. Right? And then how awesome you're going to be at 3-6 because you're going to be matrix experts. All right, guys. Well, thanks for keeping it fun, even on the chat. And we will talk on Monday about matrix multiplication. Have a great weekend. All right. Bye, guys.